Hello, everyone, and welcome. And thank you for being here today as we host our Pathways in Robotics webinar. My name is Devin Simmons, and I am thrilled to serve as the STEM Lyceums Program Manager. I'm excited to dive into today's event, and I encourage you to take notes throughout the session to capture actionable tips that'll help you in future endeavors. More information on the Center for Excellence in Education. CEE was founded in 1983 by Joanne DeGennaro and the late Admiral H.G. Rickover, who was the father of the nuclear navy and civilian uses of nuclear power, with a mission to nurture high school and university scholars to careers of excellence and leadership in STEM. CEE's mission is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics, and encourages collaboration between and among scientific and technological leaders in the global community. You may visit CEE's website to learn more about the center's cost-free programs for students and teachers, such as the Research Science Institute, the USA Bio Olympiad, Teacher Enrichment Program, and STEM Lyceums. More about the programs CEE offers. The Research Science Institute, or RSI, is a highly competitive 6-week summer science and engineering program open to rising high school seniors. Juniors are also eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. The USA Bio Olympiad, is the premier biology competition for high school students in the United States. It provides the motivation, curricular resources, and skills and training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USA Bio Olympiad in 2003, every member of the USA Bio Olympiad team has medaled at the IBO. The Teacher Enrichment Program, or TEP, provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. And then STEM Lyceums is the newest initiative at CEE. It's a virtual club for high school students to engage in discussions of exploration of STEM and concepts of career pathways. It also provides scholarship and internship resources to students nationally and internationally. And now, before we get started, I have the pleasure of introducing today's speaker. Today, as our speaker, we have Eric Dixon. He is the Autonomy and Artificial Intelligence Research Science Senior Manager for the Autonomy and Robotics Department, Lockheed Martin Advanced Technology Center. He manages a team conducting scientific research and engineering in the areas of autonomous systems, reinforcement learning, deep learning, and robotics, and manages a portfolio of R&D programs in the areas of autonomy and robotics, and develops and implements a technical vision and strategy for autonomy and robotics gen after next R&D. He earned a bachelor's degree in electrical electronics and communications engineering from the University of Washington and a master's degree in electrical electronics and communications engineering from Santa Clara University. We are so pleased to have Eric Dixon.
At Lockheed Martin, we're headquartered in Bethesda, Maryland, and we're a global security and aerospace engineering company that's principally engaged in research, design, development, manufacture, integration, and sustainment of advanced technology systems, products, and services. So Lockheed Martin consists of 4 business areas. There are aeronautics, which makes the F-35, missiles and fire control, rotary mission systems, and space systems, which is the business area that I'm from at Lockheed Martin. Inside space, we have several areas, lines of business. One of those is strategic missile defense, commercial civil space, and national security space, which covers military space and mission solutions. And then I work at the Advanced Technology Center, which is the research arm of Lockheed Martin Space, where we develop discriminating capabilities for our lines of business and our customers. Advanced Technology Center, it's been around for some time. It's been over 60 years. It's our R&D organization for LM Space. And some of the original anchor programs that came out of it were Fleet Ballistic Missile and the Corona program, one of the first remote Earth observing satellite systems deployed. So we are headquartered in Palo Alto, California, at the heart of Silicon Valley. But we do have offices throughout the United States, as you can see here, some in Colorado and Massachusetts, and several in California. So we are approximately 500 scientists and engineers and have the responsibility for developing the future for space business areas. So we're working in all types of things, from quantum, AI, data exploitation, hypersonics, materials, electronics, science instrumentation, advanced materials, robotics, cryogenics. If you name it, we're doing it. And it's a very exciting place to be. And it's a really fun place to work. And it's the pointy end of the spear for developing the vision for the future. So there are probably two things we do at the lab. One is to envision the future and the capabilities that our customers are going to need. And the other is developing those capabilities to invent the future. So that's a quick overview of Lockheed Martin and where I'm at the Advanced Technology Center. Now I'm going to go over a quick overview of how I got to where I'm at, the pathway to robotics. So as stated, I went to the University of Washington, developed an automated PCR reaction robot, worked on one at the genomics lab at the EE department at UW. It was a summer job, so I think this discussion is for aspiring engineers and roboticists and AI practitioners. And so one thing you do when you do go to college, you should take advantage of the opportunities to work on campus inside the labs, because you'll get a lot of hands-on experience. You get to work with a lot of your peers, you get to work directly with the professors and have a lot of good opportunities and a lot of fun there. So in this area, the first robot I got to work on, it's basically was automating PCR reactions, which are polymerase chain reactions used to in the process of mapping out the genome. So it multiplies the DNA that was in that reaction, and you put over a gel and put a voltage across it, and then the DNA goes across the gel, and you can measure the bands of the DNA and understand its makeup. What was neat about this is that the capillary tubes were on a cassette, and we used piezoelectric motors to basically shoot the molecules or droplets of the reaction into the capillary tubes. Capillary tubes are like these little thin glass tubes. They're very thin, very small, into it, and then we would thermal cycle them and then take them out and put them into gel. And my job there was to automate the mechanical engineering automation of taking the tubes and putting them in the gel, injecting them into the mold, and then releasing the reactants into the gel so that we can do the electrophoresis with it. After I graduated UW, I went to work at Lockheed Martin Space over in Sunnyvale, California, and got the opportunity to work on theater high altitude area defense. That is a missile defense system for the Army. And that opportunity enabled me to learn how to do system engineering, do cable design, EEE part selection, circuit card design, FPGA development. And FPGA development was new at that time. I'd done some microcontroller work, but FPGA development is definitely something we do quite often at Lockheed Martin, and it's one of the main type of ICs we use for development. And I think any aspiring roboticists should know how to do microcontrollers or program microcontrollers. I mean, you're all using Raspberry Pis now. You're all doing things with NVIDIA GPUs. And so that was kind of the start of those. But I think you're all probably on that path. And if you're not, you should start getting your hands on a Raspberry Pi and Arduinos and playing with those. So then I moved on to the Advanced Technology Center, which had a program called Gravity Pro B. So at Lockheed Martin, they have these opportunities for new engineers to rotate into new programs. Gravity Pro B was a science experiment to prove Einstein's theory of relativity. And that opportunity, I got to go on the tail end of the program. So they had already built most of the spacecraft at that time, and I had opportunity to work on solar array deployment tests, as well as various GSE type activities to make sure the spacecraft was healthy, and that every time they added additional components to the spacecraft, that it was operational and on its way to being launched. And that was a great fun experience, time up there at the ATC that made me want to go back there, because I like the lab environment, because ATC is kind of like a college lab in some respects with the type of work we do up there. So at the same time, I started getting my master's at Santa Clara University, and then I got the opportunity to go work on NIRCam up at the ATC, which is a near-infrared camera, which is on the James Webb Space Telescope, which is operational right now. And if you get a chance, go check out some of the great pictures it's taken. There's one over here on the right-hand side of the chart deck. And so NearCam is shown here on the left-hand side. It's a science instrument that has several mechanisms on it. One of them is a focus adjustment mechanism, the filter wheel mechanism, and then the pill pupil imaging lens. And so my role was to develop the electronics and the control algorithms and all the FPGA code to control those mechanisms for the telescope, as well as keeping track of heating and cooling the instrument so that it survives its environment in space. And so with that opportunity, I got to learn all aspects of spacecraft component design, assembly, integration, and test, and all the way through flight operations. And I do occasionally still get calls about things that we have to check on. There's anomalies that we can check on and make sure it's okay. That was one of my favorite projects, and I learned a lot on that project, on all the way how to do spacecraft development and instrument development all the way through from concept to the end of operations. So then I got the opportunity to go to work on SBIRS, space-based infrared system, geo satellite, and worked on the uplink downlink unit, and was able to design the communication link between ground and spacecraft. So I got to learn about how do you communicate from Earth up to a spacecraft, how do you then disseminate that information out to the different payloads that are on the spacecraft, and how do you ensure that you at all times can maintain a communication link to Earth. That was a great experience as well. Next, I got to work on the mass spectrometer for planetary exploration called MASSPEX. And so this is a science instrument on the Europa Clipper spacecraft that just launched recently. It's on its way to Jupiter. It'll be there, I think it takes about 6 years for it to get there. And so it'll be there, and it's going to orbit around, do flybys of Europa, which is a moon of Jupiter. And Europa has it's an icy moon, but there's an ocean believed to be underneath it, and it's volcanically active or geothermally active. And so the thought is that there could be life on it. And so this instrument will be taking samples of the exosphere of Europa to determine if it carries the building blocks of life on it, which is pretty exciting. And on that one, I got to design the high voltage power supply control FPGAs. Takes a high voltage power supply to energize the mass particle across the instrument, and then based on the time delay, you can determine the mass of that particle, and then ultimately, because you know the mass, then you know what element it is. I also got to work on a geostationary carbon cycle observatory called GeoCarb. So this is an instrument that would be in geo, which is over the Earth at all times. As the Earth rotates, it rotates at the same time it does, and can map continental United States as well as South America, and it keeps track of all the carbon sinks and sources of the Earth. So, you know, what are the humans, us, you know, releasing into the atmosphere as far as carbon, you know, the methane, CO2, as well as what about the sinks, which is, you know, the Brazilian rainforest is sinking that carbon, bringing that back in, and, you know, keeping the Earth more cool. So I got to work on the readout electronics of that. Basically, how do you read out the focal plane array? Focal plane array is basically the camera of that instrument. And so for any robotic system, you do need to be able to do perception. You need to be able to control it. And so all these projects allowed me to get opportunities on how to read out a vision system, control certain aspects of the spacecraft, which essentially is a robot, and then go into my next role. So I'm going to go over a couple things here that we're working on at the Advanced Technology Center at Lockheed Martin. At the Lockheed Martin, we're working on in-space servicing, assembly, manufacturing capabilities. And so ISAM will be used to manufacture and assemble very large structures up in space. We have an issue with being able to launch enough material, enough large structures up in space. And so eventually we're going to have to build them up in space. And so robotics are going to be required to do that. And in order to do that, you need to also have the autonomy to assemble those structures and be able to handle any dynamic things that might occur up in space as you're doing an assembly. So one of the projects we did was with NASA over here on the right-hand side was how do we use robotics to do plant tending on the Deep Space Gateway? And so this project coupled with universities as well as NASA, and what we had was an operator in Denver operating the robot. So this is all teleoperation, and with automated positions that it would go to in between as commands. And so with this particular robot, it can change out its end effectors, grab up different end effectors to do mapping. So we just saw a camera being used to map out the plant, to understand the structure of the plant. Then that took some tweezers to clip the plant, take a sample, maybe harvest the plant for astronauts' future use. So the idea was that Deep Space Gateway is not inhabited 70% of the time. So during that time, we could be growing crops and harvesting food for the astronauts before they get there, have it prepared for them, and then for them to be able to eat it. So this can all be teleoperated from Earth, and using a robot to then tend the plant and take care of the greenhouse there. And so at our lab, we're trying to move up the levels of autonomy. So we've gone beyond teleoperation at this point, being able to handle dynamic obstacles inside our work environment with a robot and be able to path plan and move around them, and also identify obstacles and items that we want to pick up based on object ID capabilities that we've developed. So another project we're doing is rover autonomy. So this is an autonomous rover. We see that autonomous rovers will be required for any type of lunar operations in the future. And this particular development was targeted for the Lunar Terrain Vehicle Services contract out of NASA. And this is older video here, but it's our initial work on how do we map out an environment autonomously. How do we detect obstacles, even dynamic obstacles that we can see here. We have one of the folks that work in the lab jumping in front of the robot, causing it to move around and remap and repath plan its route around the obstacle to get to the required destination. And so being able to have an autonomous vehicle that can operate on the lunar surface, collect samples, explore, deliver materials to astronauts, etc., is something we think is going to be needed in the future, not too distant future, as NASA returns to the moon with the plan to be there permanently. And so we're actively developing the technologies to autonomously drive around on the moon. Another area we're doing research in is called fail active autonomy. So for deep space exploration missions, there are times, or there are events that can occur where you won't have communications with your instrument or with your spacecraft. And as we go further out, the latency between communication links increases. So between us and the moon, Earth and moon, it's quite short communication distance. But if we're going to go explore like Europa, actually go land on the icy moon, it could be up to an 1.5 hour delay round trip for information to leave the satellite, get to Earth, ground operators read it, and then send information back over to the spacecraft. And so if you run into an anomalous condition, the spacecraft itself could be in trouble and not be able to, or instrument or lander or rover, whatever it is that we put on this icy moon or in this deep space exploration environment, will halt, and all science operations would halt in the current context of how we do things. And so we need autonomy to be able to identify the anomaly, explore the environment, and then determine what is the right resolution to that anomalous condition. And so one of those cases occurred on OSIRIS-REx, where the spacecraft was going in to take a sample of the asteroid Bennu, and as it went in, you can see it here in this GIF that it captured the sample, but there was it almost got stuck because we didn't expect the surface to be so loose. You can see how it just kind of went right into the asteroid Bennu. And so because the engineers designed the control algorithm for OSIRIS-REx to overcome that amount of force, and there's enough gain and phase margin in that design, it was able to pull back out of the asteroid, collect the sample, and then deliver it back to Earth. So the asteroid Bennu sample is already here on Earth. But this is also something we developed at ATC, was the ability to approach the asteroid, get as close as we are, and determine the best spot for us to make this sample collection. And what we're developing now and looking at is the ability to overcome such anomalies. So Carl is called causal and reinforcement learning, is a capability we're developing here at the ATC. And its goal is to detect, diagnose, and resolve anomalies. And so it's a combination of neural networks and AI algorithms and autonomy algorithms that allow Carl to collect observations into its vision model, understand what those are, and update its memory model of its known state and expected current state, and then use causal models to then determine what is the cause of a particular anomaly, and then have the controller model perform actions in the environment to help explore and understand what's happening in that environment, and then update its memory model, etc., in this loop. And that way, you don't have a system that completely halts operations and sits there and waits for a human intervention to come in and tell you what is the cause of the anomaly and how to resolve it, or walk through a fault tree with that science instrument. So anyways, those are some of the things we are working on at Lockheed Martin, and hopefully that's piqued your interest. And I think I'm at the end of my presentation here, so I will stop sharing and turn it over to Devin, see if there's any questions.
Well, thank you so much first, Eric, for taking the time again to talk a little bit about what you do, how you got into your career, and everything that Lockheed Martin is doing. And so now I'm going to open the floor for any questions that any of our viewers may have had. And while I wait for those, I do have some questions for you, Eric. And I guess my first question is just everything that you're working on. Is there a particular project or thing that you're working on that you favor over the other things that you worked on or are currently working on right now?
Yeah, I would say my favorite type of things to work on are the mobile robotic units. So any type of robotics unit that allows me to I guess develop a control algorithm or develop a perception algorithm capability to move a manipulator, or move a mobile unit is the most exciting thing to do. Most of the time, I don't do that. That's I work with my team to do that, but help influence them on the path to go. But that is definitely one of the most exciting projects, is working on mobile robotic units.
I mean, that does sound very exciting to someone, especially me. I have no experience working with robotics, so that is a very interesting and does sound very exciting. We do have one question, and I don't know if you would be able to answer this. Is more so on the Lockheed Martin side. The question is, are there any high school internships available at Lockheed Martin? I know they have several scholarships that go out, but internships, do you know if they have any?
Yeah, I can talk to that a little bit. So yeah, we do offer high school internships. It's kind of dependent on the hiring manager who's going to bring in the person to come work with them, and depending on the work that we would have that person do. But we do, like, even at the Advanced Technology Center, we do have high school interns that will come in and help us do work. And so they do have to be local generally. But that's usually how we do it. But I think any Lockheed Martin facility has that opportunity because it's available at space. And so, we'll give the high school interns interesting things to do. They can become a productive member of the team and help us develop the technologies or help us research whatever we're working on. And so that opportunity is definitely there. And we also offer college internships as well. And that you can come work with Lockheed Martin engineers and scientists and help us develop the products that we're working on.
And
And
would they be able to find that on your web on the Lockheed Martin website if they just do a quick internship? search on the search bar?
I think so. I
Okay.
haven't looked myself, but I would think so. And then, I can always do a follow-up. I can talk to some HR folks and see if there's some more information I can direct people to if they're interested in that.
Absolutely. Absolutely. And to that person that asked that question, I'll do some research myself and try to find it for you so that I can send it in the follow-up emails that go out after this webinar. There is another question that says for high schoolers, charting a path in terms of picking the courses majors or slash majors, what undergrad degree slash major and graduate degree will help set the ball rolling into robotics?
So robotics is definitely a combination of many disparate fields, right? So a double E degree, computer science degree, computer engineering, mechanical engineering, all of those will definitely go down that path of robotics. I don't know if they offer autonomy or AI type degrees yet, but we use all aspects of that. So taking courses in kinematics, understanding you have to definitely understand your physics, right? You gotta take all the physics classes, right? Doing computer vision, doing circuit card design, electronics design, perception, and understanding how to do neural network optimization as well, because you might be trying to deploy an AI algorithm on an edge device, and you don't have your high performance with computer with access to all the AWS GPUs
Mhm.
known to man. uh, could be the product you're working on. So there's all types of coursework and courses that you can take and be a member of a team of a roboticists and autonomy engineers. But I think those courses, double E, CS, computer engineering, mechanical engineering, those all lead down this path. Aerospace engineering as well can lead down this path. There's a lot of aerospace engineers that I've hired into my group.
Yeah, I think there's a lot of different ways to get there. It's just all about applying yourself. And I think what you mentioned earlier about just going to the lab at early on, and when you're in college is the best way to do that. And so do have another question is, you deal a lot with robotics and they're very high functioning, very smart to say, but how do you approach balancing human oversight with machine autonomy, especially in high stakes missions?
So in high stake missions, I don't think we're at that point yet where we're going to completely turn over decision making to the autonomous system at this point.
Okay.
We're working our way there, but I don't think we're fully there to completely turn over that all decision making to an autonomous system. So there's still an element of humans in the loop, and in some cases maybe human on the loop, but they're definitely not off on their own making decisions yet.
I, the way that it's looking, it seems like we're getting there every single day, but I know that hopefully it doesn't get to that point quite yet. And so then I just have one last question. If anybody else in the chat has any more questions, with the work that Eric has done, or maybe some of how he got there in terms of the college courses or things of that nature, feel free to ask. And after we wrap up, if you don't have a chance to ask that question, feel free to send it over to me and I can ask him for you. Um, but my last question is, what challenges do you anticipate as robotics technology becomes more autonomous? As you mentioned, we're not all the way there yet, but what challenges do you anticipate as we sort of work towards those steps?
Mhm. Yeah, I mean, it's the challenges we have currently. It's that how do we trust the system? A lot of these neural network capabilities and the like LLMs. I mean, they're hallucinating. They're non-deterministic systems, and so I don't think there's a way to fully test them, and so it's designing and developing the um, the ability to uh, test it to a point where you trust the system, and then there are stops or safeguards for the system when it hallucinates or misinterprets and perceives information that it receives. And so that's still a consistent problem. It's been a problem in this area for over 4 years, and I don't think it's fully resolved. And it's something we're still working on. It hasn't been solved yet. I mean, so maybe these future students will helps us solve it.
Let's hope. And that's a big plug for you all. There's still some things that you guys can work on as you get into these careers. And so my last question that I have from the chat is how to set pathways for AI surgical robotics. So, you can speak on that.
Sure. Yeah, so I think the question is that you're interested in going into a career where you're making surgical robots.
Hmm.
And so I would say, if you're a high school student now, and if you have the free time or you have science projects that you need to do, take advantage of the low cost of microcontrollers and the development environments that exist now. So get your hands on a Raspberry Pi, get your hands on an Arduino. Think of a science project engineering project that you could do as part of high school, maybe become part of a first robotics team, right? And get your hands dirty developing a robotic system in that way. Um, Writing the code, learn Python, learn C++. Coding is a must. I mean, I don't think I mentioned that, but every career now basically requires the need to code. You need to know how to do that. And so then if you want to go down that path a little further, you should try to get an internship, right? Get a high school internship or a college internship with one of those surgical robotic companies. Might even do some undergrad work in biology, as well as some of the work that you might take if you're going to go become a doctor. So you understand the anatomy, the physiology of humans, and understand where the gaps, where the problems that surgeons have. I mean, you can even talk to your family doctor. What are the things that they do not that they wish they had help with, basically, a robotic system that would help them there. But I think, yeah, starting out with just the tools that are in front of you or the capabilities that you can easily get your hands on nowadays, and go through some of those tutorials on how to develop a robotic system.
Absolutely. And I think a common theme throughout all of our webinars, and this is to all of the attendees, is that if there's something that you're interested in or you want to try to figure out, it takes someone, you have to take that step out and step out of your comfort zone. And like Eric said, maybe ask around in your community in ways that you can help, especially if it's that AI with surgical robotics. See what your doctors may need, see if you know any physicians or any surgeons or anything like that, see what they may be lacking or what they're always wishing that they had, and then you can go from there. But it just takes taking that step out and figuring it out and then never just giving up once it gets hard because life will get hard. And so that is the end of our question and answer portion. Again, if you do have any questions, please, please, please email them to me. I will be doing a follow-up email after this webinar is over, which you will be receiving tomorrow with our webinar survey. So please fill that out as well. And now I'm going to share my screen for the last time. And I'm going to there we go. And so again, I want to say thank you to Eric Dixon for taking this time out to speak to our students. And another thank you to all of our sponsors, including the Claude Moore Charitable Foundation and Lockheed Martin for helping put together this webinar and the STEM Lyceum program. And I want to say thank you to everyone for joining us today.